So Blaine has talked about Detlef's work on sectional curvature. Detlef was also very much involved and interested in studies of manifolds with Ricci curvature, so non-negative Ricci curvature. And his work has been very significant and influential in these initial studies trying to understand what Ricci curvature is. So his works are really foundational and led towards influencing the modern directions that are currently being pursued in Ricci curvature. So things started off with this splitting theorem. The splitting theorem is one of my most favorite theorems in geometry. Many of you know what the statement is. The statement is very simple. It says, so this is due to Detlef Gromoll in 1971. Suppose you have a complete manifold of non-negative Ricci curvature, and suppose you have a line in that manifold. So a line is strengthening of the rays that Blaine was talking about. So a line is a complete length minimizing geodesics. So an embedding of the whole real line into the Riemannian manifold, such that every finite piece of that line is length minimizing. You realize the distance between the endpoints of those segments. So if you have such a isometric embedding of a line into the R factor inside this Riemannian manifold, then that Riemannian manifold splits along that line, in the direction of that line, isometrically as a product. So this may not seem as that interesting or that strong path when you first look at it. In fact, the earlier result was Toponogoff, which proved this result in the context of non-negative sectional curvature. In fact, if you look at their paper on the splitting theorem, the very first sentence just starts as follows. It says, the purpose of this paper is to extend Toponogoff's splitting theorem for manifolds of non-negative sectional curvature to manifolds of non-negative Ricci curvature. So it gets straight to the point. It talks about the origin of where this came from and what they're going to do. Nevertheless, the importance of this result versus the importance of Toponogoff's splitting theorem are vastly different. Toponogoff's splitting theorem for non-negative sectional curvature is a very nice theorem, but it's more of a consequence of more fundamental tools. There are many more tools and methods available to study non-negative sectional curvature, as Blaine was talking about. Things like Toponogoff comparison theorem, convexity, and things like this. So using these multitude of tools for sectional curvature, you can gain a lot of information, a lot of structural results that Blaine has been talking about. With Ricci curvature, there are many, many fewer tools available with which to understand the structure of manifolds of non-negative Ricci curvature. And in fact, at least classically, up until the last decade or so, there are really only sort of two tools that one can use to understand Ricci curvature. The first one is the volume comparison theorem to the Bishop and Gromoll, and the second one is the splitting theorem. So the splitting theorem really plays a central role in understanding the structure of these types of manifolds. Let me describe briefly what the proof is. The proof is different. Proof has analogs with the Toponogoff proof, but it's also has fundamental differences. So it introduces some basic new ideas and techniques that are very important for future work. So you consider a ray. So you start off with your ray that you're given. You have this line gamma, but just look at one half of that line. So these are the rays that Blaine was talking about. And with this ray, as in Blaine's picture, you consider this function here. So you fixed your base point gamma of 0. The line starts at time 0, and you look at the distance of point x in the manifold to the initial point of this ray, and renormal it. As t goes to infinity, this distance here goes to infinity, so you don't get anything in the limit, but you can renormalize this distance function by subtracting off this t. So this is a construction that goes back, I guess, into the 30s or 40s. This is a construction due to Bozeman, and if you take now the limit of this sequence of functions as t goes to infinity, this is a family of functions parameterized by t. The triangle inequality implies that these functions, as functions of t, are monotone increasing in t. So you have a monotone increasing family of functions in t. They have uniform upper bound, and so you can pass to a limit. And the limit is called the Bozeman function associated with this ray. Now, as you know, when you have distance functions have cut points, and so they have singularities, and the singularities contain a lot of information about the structure of the manifold. You can't, by no means, ignore them. And so, because of that, this limit function, the cut points, cut locus can get sort of relatively complicated. Cut locus of the point gamma of t. And so when you take this limit, you have a limit function which is not necessarily very smooth. So in general, you can do this construction on an arbitrary Riemannian manifold. Ricci curvature hasn't come in yet. And this limit Guzman function is just a continuous function. It's a C0 function. You don't know anything in general about its differentiability properties. So the basic tool that Chiger and Gromoll established is the fact that this Guzman function, G gamma, is superharmonic. So in some sense, that means the Laplacian of this function is less than or equal to 0. But you have to make more precise, you have to say what this means, because G gamma is only a C0 function. You can't take any of its derivative. So the way this is done, it's done slightly differently than the original work that Chiger and Gromoll did, but it's more or less just a rephrasing of their proof, or putting the proof in slightly different language. The essential ideas are in their paper. So what shows this inequality, what it means by this inequality is this Guzman function is superharmonic in the sense of support function. So what's a support function? So here you have your geodesic ray, gamma, starting at gamma at 0 with initial velocity vector here. These sequence of points ti are going out to infinity. And you want to study the behavior of this Guzman function G gamma in the neighborhood of this point x here. And so what you can do is to take first of all, construct a minimizing ray, a ray starting at this point x, in the same way that Blaine mentioned earlier. So you take a sequence of points ti going to infinity here, and look at the minimizing geodesics from x to ti. The sequence of tangent vectors has a limit, and you get a limiting tangent vector. That limiting tangent vector is a tangent vector to a ray. So here, a ray here, sigma, in some sense sort of parallel to the initial ray gamma, but based at an arbitrary point x instead of 0. And so now, given that picture, you form the support function is then defined by this process. So you fix your base. You want to look at a support function for this ray based at this point here. So you're fixing now this point. We're going to say the geometry of this function based upon this Guzman function based at this point. So it's geometry nearby x. And so you consider this function here. You fix x, you fix t, and you let y vary. Notice that this difference here is just like a Guzman function again. So this distance function from sigma t to y minus t is the same thing we did before, Guzman type function construction. So this is sort of like a sum of approximation to a sum of two Guzman functions, one based at x, one based at y. Now, the reason that's nice to do this is because when you use the function of y, fix x and fix t, you use the function of y, this function is now smooth in a neighborhood of x. When y is equal to x, this distance here is just equal to t. Sigma is a ray, so the distance of sigma of t to sigma of 0, which is x, is t minus t is 0. So these two functions here agree when x equals y. And because this is a ray, the point x is not conjugate to the point y, so there should be a point y here. So when x equals y, so sigma t is a ray, so sigma t is not, x is not in the cut locus of sigma t, so that means that this function is smooth in the neighborhood of x. So if y is near x, this function is smooth. As I just said, these two functions agree. An easy argument with the triangle inequality tells you have this relation between these two functions. So this characterizes what it means to be a support function. The picture roughly looks like this. You have this, here you're looking at the behavior of your function g gamma at a point x, and it's just a continuous function. You can't take any of its derivatives. The support function for that function g gamma is another function, which schematically looks like this green picture. So the two functions agree at the point x, and the support function is bigger than or equal to your given function, your given C0 function, nearby that point x. So this means so the difference here is gxt minus g gamma is non-negative. So that means in some sense the Laplacian should also be bigger than or equal to 0. Okay, so now the support function g is smooth, so you can talk about its derivatives. Now you can calculate, just by using comparison geometry, calculate the Laplacian of this distance type function g of xt.
Mike, could you slide it up so others can see?
Sorry. So because this function here is now smooth, and it's a distance type function, you can use standard methods in geometry that go back to the earlier days and calculate this, estimate its Laplacian from above. This is the volume comparison theorem type argument. And you can easily find out the Laplacian of this function is also equal to n minus 1 over t. And since t is now getting arbitrarily large, this term here gets arbitrarily small. So this is true in a smooth sense, just by a classical computation. And this is the meaning of, you don't know what this statement here means, but this statement here means that there's a support function which satisfies this inequality. All right. So you have this notion of superharmonic functions which are just continuous. It means just what's stated there. So these Boltzmann functions are superharmonic in the sense of support functions. That's already established. So now for the proof of the splitting theorem itself, now suppose you actually have a line. So we were working with just a ray before. Each ray gives you an associated Boltzmann function. So now suppose you have actually a line. So you have a line has its two halves, its future and its past, or its forward and backwards in time. So you have these two rays associated with that line, gamma plus and gamma minus. And from that you form g plus, the Boltzmann function in the future direction, and the Boltzmann function in the past direction. Now you want to look at how these two Boltzmann functions compare with one another. The triangle inequality is just that picture up there. This distance plus this distance, that's this geodesic plus this geodesic. Some of those two distances is bigger or equal to the straight line distance here, which is that distance s plus t. The triangle inequality says this sum here is non-negative always. And of course you have equality if point x lies on the line gamma. So you reach the borderline case here for points x which are in the line. This is now preserved under limits, this inequality here. And so therefore for the limits of these Boltzmann functions, some of these two Boltzmann functions, the future and the past, are non-negative. So this is a function which is non-negative, and it realizes its minimum exactly on the line, at least on the line gamma. But what we just did by the comparison geometry type arguments, the future Boltzmann function is superharmonic as well as the past. So both Boltzmann functions are superharmonic. Therefore, their sum is superharmonic in the sense of support function. And now you can use a maximum, or in this case a minimum principle. It's an extension of the classical maximum principle for superharmonic functions, which are smooth, but an extension of that to the maximum principle in terms of support functions. So the generalization of the classical maximum principle due to Hopkins-Lobby, which says that if you have a superharmonic function which realizes its minimum at some point, which is the case here, then that superharmonic function has to be globally constant. And the constant is equal to its minimum value. Since the minimum value here is 0, that means this superharmonic function is in fact globally 0. So now since it's globally 0, so this process now has extended the information you had nearby this line here. This function vanishes on the line now. The maximum principle tells you it vanishes globally everywhere. That's a very strong piece of information. These two functions now are just negatives of each other. They're each superharmonic, therefore each one is harmonic. So you have now a pair of harmonic functions. These are basically distance functions. The harmonicity tells you that they're smooth. The regularity theory for harmonic functions is something that is now smooth functions. So now you forget about this plus and G minus have parallel gradients. The gradient vector fields of these smooth functions are parallel, and that parallelism gives you the split. So it's a beautiful proof, and it's been highly important for understanding Ricci curvature ever since it was initially done.
Where does the Ricci curvature come in?
Well, so it comes in here. So when I mentioned these sort of volume comparison estimates. So you want to get this estimate for the Laplacian. The Laplacian is something for this. This is more or less the same thing as saying Ricci curvature is not negative.
Also the Bachman
argument. It's also used in the Bachman argument. Thank you. Should I put it on?
We're just asking.
Can everybody hear me okay?
Put the mic on.
Okay. Is that any better or any different? Is that the same? Okay. The next topic on Ricci curvature is, so when Detlef was one of the first people to explore in detail manifolds of positive Ricci curvature, just as he was also for sectional curvature. And one of the most important aspects of Detlef's career is the wealth of students that he's had. He's had a huge number of students who have gone on to have done very nice work in their own right. And I guess around the 70s especially, maybe also into the early 80s, a number of his students were working on manifolds of positive Ricci curvature. So these people here, Hernandez Andrade, Paul Ingram, Nash, Bohr, and
Oh, it's another name.
I think it is John Nash, but it's different. Obviously, not. So these students of his were obtained a number of examples of manifolds of positive Ricci curvature on various kinds of bundles over compact manifolds, and also on various kinds of submanifolds of Euclidean space, particularly the Reese point varieties, which were the rage in the 60s and 70s. One of the questions fundamental questions Detlef was interested in at this time, and shows you the state of knowledge that he was grappling with in this era, was, does any manifold with positive Ricci curvature admit a metric with non-negative sectional curvature? So this is a very simple, kind of obvious question. Nobody had the faintest idea of the answer to it. They're trying this and trying that, and it was an open question for quite a while. And then in '83, I guess apparently Detlef, with a Humboldt Fellowship, visited Münster, and he and his old friend Wolfgang teamed together, and were the first people to provide examples of non-compact manifolds of positive Ricci curvature, which you can prove they do not carry or do not admit any metric of non-negative sectional curvature. The way this is proved is, of course, by the Soll theorem. So the Soll theorem says any manifold of non-negative sectional curvature has to be a vector bundle over a compact manifold. And so their examples have a topological structure that are not vector bundles over compact manifolds. They're open manifolds which are somehow topologically exotic in a sense, not being vector bundles. A few years after that, sort of the floodgates started to open. So this work of Detlef and Wolfgang was the first instruction to illustrate, give an answer to this question. A few years after that, sort of the floodgates started to open, and many more kinds of examples poured in. So first, Shah and Yang proved that there were metrics of positive Ricci curvature on connected sums of these spheres. Actually, they did this in higher dimensions, dimension 7, and then actually I did prove that this was true in dimension 4, S2 cross S2, so in 1990 or so, and then a year after that they did this for all dimensions.
So all these manifolds admit metrics of positive Ricci curvature. These are compact manifolds, not non-compact manifolds. And the way you know that these manifolds, so you construct these metrics by hand, by explicit construction. And the way you know that these manifolds don't have metrics of positive sectional curvature on them is by this marvelous theorem of Gromoll, this Betty number bound, that manifolds, compact manifolds with non-negative sectional curvature have a universal, in a given dimension, have a universal bound on their sum of all their Betty numbers. The sum of all Betty numbers is just bounded by some fixed number. And the Betty numbers here can get arbitrarily large. There are also examples of Xia and Yang on these kinds of manifolds. You take R4 cross S3 and glue in S3 cross CP2s. You can do this infinitely many times and construct manifolds of positive Ricci curvature, which are of infinite topological type. There are also examples due to Claude Lebrun, Peter Kronheimer, and myself, examples of this type of infinite topological type manifolds, which are actually Ricci flat and even Taylor. So you can put on very, very strong restrictions with Ricci curvature and infinite topological type. So there are many more examples of this. There are later examples by Perelman, important examples in this category. A student of Toby Colding, Mendwi. A good number of other people have also worked on furthering our understanding of constructions of manifolds of non-negative Ricci curvature. It's still an open area. There's still many interesting problems, further work to be done in this direction. Okay, so now there's this wealth of examples of manifolds of positive Ricci curvature. Many more complicated topological types can occur than in sectional curvature. So there's a question of, can you now, from the other point of view, turn the tables and get a handle on any kind of structural theorems or that you can obtain for manifolds of positive Ricci curvature. So this was another interest of Detlef's. So are there situations where you can sort of get some control on topology? Of course, you have to add some hypotheses, but can you find nice hypotheses which control the topology of manifolds of non-negative Ricci curvature? So again, the Soule theorem says that all open manifolds of non-negative sectional curvature are of finite topological type. They're just diffeomorphic to bundles over compact manifolds. We know such situation can't hold, is very far from holding for Ricci curvature. But can you get some kind of finite topological type result for Ricci curvature gas among our hypotheses? So I guess also the first result in this direction is due to Detlef with Uwe Albrecht in 1990. The statement goes as follows. So suppose you have a complete open manifold with non-negative Ricci curvature, and suppose that this manifold has control on how its diameter grows as you go out to infinity. So what this means is, this is illustrated in this picture here. So you have take an arbitrary period, you have a sort of picture of a complicated open manifold. You can imagine the complexity getting arbitrarily. As you go further and further out, you have more and more branching, more and more ends. Things are getting more and more complex. Take any fixed base point, arbitrary, just fix it, and look at the boundary of the geodesic ball of radius r, centered at this point here. So you look at all points which are a distance equal to r in your manifold from this base point P. This is a collection of a closed subset denoted by sigma of r here. So schematically drawn in green here like this. And so this is the sphere, the geodesic sphere of radius r. It need not be smooth or anything. It can be quite a complicated closed set. So now you want to look at the diameter of that sphere of radius r. So there's various ways to do this, but the natural way to do this is to look at the diameter of this point set as a subset of a larger open manifold. And the natural open manifold to consider is, for instance, the complement of this ball of radius r over 2. So the brown region here is the geodesic ball of radius r over 2. Look at the complement of that. That's still an open manifold, an open non-compact manifold. And it has a Riemannian metric on it, and look at the diameter of this sphere of radius r within the exterior of this ball raised r over 2. So you look at the maximum diameter of each component. So you have a collection of finite number of components here, and each component type of set has its diameter as a metric space. You have to take the maximum of these diameters. And so the diameter growth condition, little o of r to the 1 over n, means the diameter of these spheres, each individual sphere, grows slower than r to the power 1 over n. N is the dimension. So this ratio here, the ratio of these two goes to 0. So the limp soup of this ratio, goes to 0 as r goes to infinity. So this non-negative Ricci curvature is diameter growth condition. Then you have to add. You also add it on a condition on sectional curvature. Sectional curvature is bounded away from minus infinity. Sectional curvature is not going to minus infinity. So, for example, you could scale things so the sectional curvature is big equal to minus 1. So if you have, so that's your hypotheses. If you have a manifold non-negative Ricci curvature with these extra structural conditions, then I'm not sure why. Then the manifold is homotopy equivalent to the interior of the compact manifold boundary. I'm not sure why Wolfgang says it this way. So it's actually stronger than this. The manifold is diffeomorphic to the interior of a compact manifold. Diffeomorphic to the interior of a compact manifold with boundary. So if you get much more than homotopy, you actually get diffeomorphic. I remember when I first saw this. In fact, I'm still kind of interested in this question. I haven't thought about it in a long time. It's an open question of so this result here sort of has a mixture of these two worlds, the world of non-negative Ricci curvature and the world of sectional curvature, because you have both hypotheses here of sectional curvature and Ricci curvature. And they're using both aspects of both areas in here. So it's an open question of whether this result is still true if the sectional curvature bound can be dropped, and what dispense with the non-sectional curvature, and have this just pure Ricci curvature. That's an open, as far as I know, that's still an open question. And it would be interesting to know one way or the other. Some of the ideas of the proof of this. So one shows that the distance function. So we have this. You can understand the structure of this manifold by looking at the distance functions. Look at the distance function, the structure of the distance function from this base point P that you specified at the beginning. So we'll get to that. But prior to that, first of all, you look at the excess function. So here's your base point P. Take an arbitrary point Q. Q should be very, very far away. And also point X, which should also be far away. So you look at the asymptotic structure of this manifold. So you think of Q and X being far away, but also X and Q being far away from themselves as well, each other as well. And so form a geodesic triangle like this, and consider the excess function, so the obvious thing, distance from P to X plus distance from X to Q minus distance from P to Q.
No.
So the excess function is going to play an important role in the proof. And one also looks at the height function, the height of this triangle, namely the distance from X to the base geodesic point Q. It's elementary to see that this excess function is non-negative. This is the triangle inequality. And a couple applications of the triangle inequality tell you the SLX function is bounded above. It's at most 2h. Of course, the excess function restricted to the line to the base geodesic PQ is 0. And similarly to what we just saw for the splitting theorem, it's a volume comparison theorem using non-negative Ricci curvature. You can compute the Laplace of this excess function as less than equal to n minus 1 times these 1 over these distances here. Again, it's sensitive barrier system, as we talked about before. So this is very reminiscent of the splitting theorem. Now, so that kind of standard, what's much less, which is much more novel, is an excess estimate for long thin triangles. So again, you should think of apply the data here are the same as the data in this triangle. So your base point P. Think of Q and X being very far away. Here you want S of X to be at least the minimum of these two distances. So you should think of these distances as being both large numbers. This indicates that you want you don't want S to be large also, and so that means you want X to be roughly in the middle. You don't want X to be too close to P or too close to Q. It should be roughly somewhere in the middle of that. Then if the Ricci curvature is non-negative, and if the height of the triangle is less than or equal to S over 2, then you would have this very novel estimate. This is quite new at the time. So the XS function has an upper bound controlled in terms of just the height of the triangle and this function S, which measures the distance of the point X to the other points P and Q. That looks rather technical, and it is, but the idea, you can see that how this is going to be used. The idea for this goes as follows. If the diameter of these spheres of radius r are much smaller than r to the 1 over n, then this diameter, think of x as lying on sigma of r, so think of x as being a point on here. In fact, the diameter of this sphere is much smaller than 1 over Rn, tells you this term here is h is much smaller than r to the 1 over n, so n power is much smaller than r. So this term here is much smaller than r. S here you can arrange to be r, it's in the order of r. So this is very small. This is small compared with r. This is in the order of r, so the ratio goes to 0. The diameter down here fits in exactly in this estimate here to tell you that the XS function of X, which these were simple points X, simple geometric configurations, the XS function can always be made to go to 0 in infinity.
This XS is like one of the most important theorems for education. I mean, it's used for all geometrical stuff.
Yes, yes. Yeah, that's a good point. Thank you. Okay, so that's one side. So the XS function goes to 0 asymptotically. On the other hand, you can use the lower bound sectional curvature to obtain a lower bound of the SX function, at least at certain points. So suppose now we have the same triangle as before, dxq. But now suppose this point x is what's called a critical point of the distance function. So this point x is now not an arbitrary point where it was before, but suppose this point's a critical point of the distance function. This is a notion of distance function is not smooth, but there's a substitute for smoothness originating in the work of Karsten and used a lot by Gromoll as well. So a point x is a critical point of the distance function from P if for any tangent vector at x, there's a geodesic from P to x whose angle between those two vectors is less than or equal to pi over 2. So it says that there, at this point x here, there are at least several geodesics, several minimizing geodesics coming into it from P, and those geodesics, the linear span of those geodesics is the whole tangent space. And so you can apply that here. So here's your base point P, here's your critical point x. This point Q is far away. Take a fixed minimizing geodesic from Q to x. Like this is a critical point now. Tell you there is a minimizing geodesic from P to x here, such that this angle here is less than or equal to pi over 2. This angle is less than or equal to pi over 2. You can apply the topological comparison theorem to get an excess estimate for, say, this triangle here. That leads to this. The excess increases. As you make a triangle bigger, the excess increases. It doesn't get smaller. So we have fixed triangles. These are minimizing geodesics. So we look at a geodesic like this and go further out, the excess just gets bigger. So you have a uniform lower bound on the excess at critical points, and this is, of course, contradiction. This says the excess can't get small if you have critical points. If your critical points are far away, the excess can't be too small.
the other hand, the previous estimates of the x-axis had to be arbitrarily small. The upshot of this contradiction is that there can't be any critical points too far away. There can't be critical points to this distance function fixed at p very, very far out. This is about critical points. Standard Morse theory type argument tells you that your manifold is fine homological type. That's proof. Okay, so yeah, I should have. Let me just emphasize again what Christina mentioned, that this excess estimate of operation Gromoll is crucial to many of the more modern developments that have been happening in Ricci curvature, starting with the work of Holding and then carried on further by Cheer and Holding and others. So it played a very foundational role. Finally, to sort of come back full circle, I'll just talk for a minute or two about periodic geodesics. Unfortunately, I know very little about this area. So I'll just remind you of some results which you may have heard about before, and if not, you'll learn something new. So again, in the 60s, Detlef was here, I guess, at SUNY Brook at the time, and perhaps Wolfgang also proved these results on periodic geodesics. So the situation is as follows. Suppose you have a closed manifold, which is simply connected, and you consider this free loop space. So the space of closed curves, not based at a particular point, but just with arbitrary basis. The sequence is free over the manifold. And suppose that the sequence of Betty numbers of this free loop space is unbounded. Then they prove that there are infinitely many geometrically distinct periodic geodesics. These periodic geodesics were studied a great deal, of course, since the time of Morse, and this uses Morse theoretic methods, but in the setting of Hilbert manifolds, which was the natural way things were done starting in the 60s. There's various tools that Gromoll and Meyer developed to implement the appropriate Morse theory. I'm afraid I can't add anything to this myself. And another issue that Gromoll and Meyer were interested in, Gromoll and Brook were pursuing somewhat later, is the following. So a metric on a Riemannian manifold is called a C metric. If all geodesics are closed and have the same minimal period, I'm not sure why we call it a C metric. You might also call it an O metric. C closed up an O. Anyway, it's called a C metric if the geodesics are closed and have the same minimal period. And if in addition to that, all the geodesics have no self-intersections, they're embedded, then the metric is called SC metric. And it's well understood that for an SC metric, the inner homology ring is identical to that of a Riemann symmetric space. And Detlef and Carson proved in 81 that any Riemannian metric on 2-sphere, all of whose geodesics are closed, is such an SC metric. So all the geodesics are simple, they're embedded, and they have the same minimal degree. And there's been an open conjecture, I guess, for some time now. If this is the case, if the manifold is simply connected and all geodesics are closed, then is G a C metric. So, and I guess I'm not aware of what's going on in this area, unfortunately. So, work hard looking has just recently proved, apparently, that this conjecture is true for manifolds homomorphic to the n sphere. Okay, so this has been a brief history then of some of the aspects of Detlef's work during this period. So n equals 3 is not done?